So here's some useful projectile equations. Let's start out with a general projectile problem. The ball is initially launched, or some object, at an angle of theta with an initial velocity of v naught. And we know that whenever we do one of these problems, we have to begin by first finding the x and y components of the velocity if they're not given, right? And so this is v naught y, and this is v naught x. And so v naught x is equal to v naught cosine theta, and v naught y is equal to v naught sine theta. And so now we can ask some simple questions. But first I'm going to write some of these equations that we've been using for the y motion and the x motion over here. I'll start with the x equations. X equals x naught plus v average x times t, and then vx is equal to v naught x is equal to v average x. The x velocity never changes for a projectile because there's nothing pushing on it or slowing it down. It's only gravity that affects the y direction. And then we've got the y equations. Y equals y naught plus v average y times time. Vy equals v naught y minus g times time. V average y is equal to vy plus v naught y over 2. Y equals y naught plus v naught y times t minus 1/2 gt squared, and vy squared is equal to v naught y squared minus 2g times y minus y naught. So those are the equations. And so I'm going to ask a few just questions that I know we can determine the answer to. And so this is the time at the top, and that's the first question we want to answer for. How long does it take to get to the top? Well, if we grab equation 2 here, so this is 1, 2, 3, 4, 5. Then if we grab equation 2, v at the top is 0. That is to say, the y velocity at the top is 0 because it's not going up or down anymore. And so we can say, look, vy equals v naught y minus g times t means that 0 is equal to v naught y minus g times t, or t is equal to v naught y over g. And that's equal to v naught sine theta, because that's what vy is. Vy, if you look over here, is v naught sine theta over g. And so that's the time to the top. And so this is, if somebody gives you the angle and the initial velocity, you can tell how long it takes to get to its top of its trajectory by just dividing v naught sine theta divided by g, right? For a flat surface, that is to say, if you're just, on a football field or on a plane of some kind, right, rather than up or down a hill, then you can calculate the time in air. That's just equal to twice the time to the top. And so that's just 2 v naught sine theta over g. It's just twice this time, provided that the surface is horizontal. It's saying it takes the same time to get to here as it does to get back down to the bottom. It's only true if the surface is horizontal. And so now we can tell, just from the initial things, the v naught and the theta, what the time to the top is and what the total time in the air is. Right? And so remember this. I'll just write it off to the side. So time to the top equals v naught sine theta over g. And then we can say the maximum height is just the value of y at this time, right? And so we could calculate that from equation 5 if we wanted to, right? equation 5 says Vy squared is equal to V naught y squared minus 2g times y minus y naught. Well, at the top, Vy is 0, and so this would just be 0 is equal to V naught y squared minus 2g times y minus y naught, right? What we want is this height now. That's what we're asking about. And that's y minus y naught, right? This is y, and that's y naught. Usually we pick y naught equal to 0, but we don't have to. And so if we solve for y minus y naught, move this to the other side and divide by 2g, we get y minus y naught is equal to v naught y squared over 2g. That's equal to v naught squared sine squared of theta over 2g. So maybe I'll write it this way. I'll write H max is equal to V naught squared sine squared theta over 2g. Right. That's the maximum height. And so if you're given the initial velocity and the angle, you can just plug into this formula and calculate it. You can go to the trouble to figure all this out, but you can just use this formula, right? These guys will be on your equation sheet somewhere. So now we want to know the range. So this, let me see if I can indicate it here. This is the range. It's from where it's launched to where it lands, assuming it's horizontal. And that's just x minus x naught, right? And so we can just grab the first equation here and say, look, x equals x naught plus v average x times time. Well, if we want to know the total distance, the range is just x minus x naught. It's how far it traveled horizontally. This is the range during its whole flight, right? And that's equal to, so v average x is the same thing as vx is the same thing as v naught x, and so that's just v naught cosine theta, right? V naught x is just v naught cosine theta times the time. Well, this is the time in the air, right? The total time in the air is how long it takes to get this to that spot, and it's just twice the time to the top, so it's times 2 v naught sine theta over g. And so the range becomes v naught squared times 2 sine theta cosine theta all over g. And you probably don't know your trig identities, but if you did, 2 sine theta cosine theta is the same thing as sine 2 theta, and so this is v naught squared sine of 2 theta over g. So if this was 30 degrees, you'd plug in 60 degrees here. And so again, this assumes a horizontal surface. This formula does. This is only valid when the surface is flat. If you were to throw it off the Grand Canyon, it would keep moving horizontally much further than this, and so it only counts when the surface is horizontal. And so the range is equal to v naught squared sine of 2 theta over g. And so those are some of the formulas for special cases. And the nice thing about them is that you can just plug them in. And so let me just give you an example here. So a ball is hit at 30 meters per second at an angle of 60 degrees. And so they're asking us for the range, right? And so the range is equal to V naught squared sine of 2 theta over g, and that's equal to 30 meters per second squared times the sine of 120 degrees divided by 10 meters per second squared. The range is 78 meters. So we can ask what angle gives maximum range, and if you look at this formula, range is equal to V naught squared sine of 2 theta over g. Well, the angle, as the angle changes, the value of sine of the angle changes. Sine has a maximum value of 1, and that happens when the thing in parentheses is 90 degrees. So R is maximum when 2 theta equals 90 degrees, or theta equals 45 degrees. And so in that case, the range is just V naught squared over g, because the sine of 2 theta is just 1. And so that's the maximum range you can get. And so, if somebody says, well, what's the maximum range of a ball going 30 meters per second? Imagine I can throw a ball at 30 meters per second at any angle, right? Then, I throw it at 45 degrees, and my range is V naught squared over g, which is 30 meters per second squared over 10 meters per second squared, which is 90 meters. So I can do a slightly more sophisticated version of that. Let's draw a plane again here, right? And here's my plane, right? And so if I draw this way, so let me just draw a shorter vector there. This is the velocity of the plane relative to the air, right? And now we're going to say, look, this is the velocity of the air relative to the ground. And so the plane is actually going this way, right? This is the velocity of the plane relative to the ground. It's the sum of the velocity of the plane relative to the air plus the velocity of the air relative to the ground. If I use the same numbers I did, this is 50 meters per second, and this one is 30 meters per second. And if I assume that this angle is 45 degrees, then I can figure out what the red one is, right? If I draw, let me just draw these guys in blue here. this line here is the velocity of the plane, the velocity of the air relative to the ground in the x direction. Again, if my coordinate system looks like this with y up and x across, right? And this is the velocity of the plane, the air relative to the ground in the y direction. I know the notation is a little awkward. Let me write that a little better, maybe. Velocity of the air relative to the ground along the y direction, right? That's this guy. And so now you can sort of see that the x component, the velocity of the plane relative to the ground, which is what we're after, right, is equal to the velocity of the plane relative to the air It's the velocity of the plane relative to the air plus the velocity of the air relative to the ground. These are all vectors, right? And so if I want to look at the components, if I want to find the components of this vector, the velocity of the plane relative to the ground, the y component is just the velocity of the plane relative to the air, because that is its y component, because the y component is up, plus the velocity of the air relative to the ground, the y component. That's this little piece right here, right? The velocity of the plane relative to the ground, the x component, is just the velocity of the air relative to the ground, the x component. That's this piece. The plane's motion relative to the air has no x component. It's the air that has an x component. And so I can figure out this guy by figuring out his x and y components, right? And so we can say, look, the velocity of the plane, the velocity of the air relative to the ground, the x component is equal to, if I say this angle is 45 degrees here, then this angle is also 45 degrees. It's 45 plus 45 is 90, and that gives me the velocity of the air relative to the ground, and the x component is the velocity of the air relative to the ground times the sine 45 degrees. And that's 21.2. And that means that the velocity of the air relative to the ground along the y direction is also equal to 21.2, because 45-degree angle has a sine and cosine that are the same. And so that says that the velocity of the plane relative to the ground along the y direction is 50 meters per second plus 21 meters per second, which is 71 meters per second. And the velocity of the plane relative to the ground in the x direction is just 21 meters per second. Since the velocity of the plane relative to the ground is equal to the square root of the sums of the squares of those two, it's 71 meters per second squared plus 21 meters per second, which is about 74 meters per second. And the angle, this angle here, theta, I guess I'll calculate it over here. Theta, am I still on the screen, equals tan inverse of 21 over 71 meters per second. Those will just cancel, right? So 21 divided by 71 . 17 degrees. So this section also on 2D motion is just on adding velocities. And so we did projectile motion a minute ago, and so now we'll look at maybe in the horizontal plane, talking about adding velocities. And so first let me do a one-dimensional one. Suppose I have a railroad car here, right? Just a flatbed car that's moving, velocity of car relative to ground is equal to 10 meters per second, right? And then I've got a person on the car who's running, and the velocity of the person relative to the car is 3 meters per second. And so if I want to know the velocity of the person relative to the ground, that's equal to the velocity of the person relative to the car plus the velocity of the car relative to the ground. And so that's 3 meters per second plus 10 meters per second is equal to 13 meters per second. Right. So I can say, suppose the velocity of the person relative to the car was minus 3 meters per second. So he's running the other way. Right. Well, in that case, then the velocity of the person relative to the ground, maybe I can find a darker marker here, is just the same. It's the velocity of the person relative to the car plus the velocity of the car relative to the ground, except now it's minus 3 meters per second plus 10 meters per second, or 7 meters per second. If the person's running in the same direction as the car is traveling, they're going to be moving faster relative to the ground than the car is. If the person is running in the opposite direction, then relative to the ground, they'll be moving slower than the car is.